Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic electrical and electronics engineering. We'll dive into key concepts like logic gates. Slide 1. Introduction to logic gates. Let's begin with the basic idea. Logic gates are the building blocks of digital electronics. They are electronic circuits that perform logical operations on one or more binary inputs to produce a single output. These outputs follow Boolean logic, which means they are either high, 1, or low, 0. Logic gates are essential in digital devices like calculators, computers, and embedded systems. Each logic gate represents a basic logical function. For example, the AND gate performs logical multiplication, while the OR gate performs logical addition. The key types of logic gates are 1. AND, 2. OR, 3. NOT, 4. NAND, 5. NOR, 6. XOR, 7. XNOR. These can be combined in different ways to create complex logic circuits for processors, memory units, and control systems. Each gate has a unique symbol in a truth table, which shows the output for every possible input combination. We'll go through them one by one in the next slides. Slide 2. AND gate. The AND gate outputs high, 1, only if all inputs are high. Think of it like this: a bulb will glow only if both switches are on. 1. Symbol, shaped like the letter D. 2. Boolean expression, output y equals a and b, written as y equals a, b. 3. Example, a circuit where both sensors must detect presence to trigger an alarm. Significance, AND gates are used in control systems where multiple conditions must be true to activate an output, like safety mechanisms in industrial machines. Slide 3. OR gate. The OR gate gives a high, 1, output if at least one input is high. It's like a bulb that turns on if either switch is pressed. 1. Symbol, curved input, pointed output. 2. Boolean expression, y equals a plus b. 3. Example, doorbell that rings if either of two push buttons is pressed. Significance, OR gates are used in systems where any one condition is sufficient to cause an action, such as multiple emergency stops for a machine. Slide 4. NOT gate. The NOT gate is the simplest logic gate. It only has one input and one output. It inverts the input, output is high if input is low, and vice versa. 1. Symbol, triangle with a small circle, representing inversion. 2. Boolean expression, y equals a bar. 3. Example, a warning light that turns on when the fuel level is not okay. Significance, NOT gates are used for inversion operations, like reversing a logic signal, useful in alarms and feedback loops. Slide 5. NAND and NOR gates. Now we look at NAND and NOR, which are derived from an and OR respectively, followed by a NOT operation. NAND gate. 1. Outputs 0 only if all inputs are 1. Otherwise, it gives 1. 2. Boolean, y equals a, b closing parenthesis. 3. Example, a system where failure is indicated only when all sensors detect danger. NOR gate. 1. Outputs 1 only if all inputs are 0. 2. Boolean, y equals a plus b closing parenthesis. 3. Example, streetlight remains off unless all light sensors read darkness. Significance, these gates are called universal gates. Any other gate can be made using just NAND or just NOR. They are widely used in digital circuit design for flexibility and cost savings. Slide 7. Applications of logic gates. Logic gates form the core of all digital electronics. Here are some key applications. 1. Combinational circuits, like adders, multiplexers, comparators. 2. Sequential circuits, using logic gates to build memory elements. 3. Digital clocks and timers use logic for counting operations. 4. Control systems, where logic gates manage machine operations. 5. Microprocessors and CPUs, millions of gates perform logic operations. 6. Alarms and sensors, for decision-making based on input signals. 7. Remote controls, encode, decode logic using gates. 8. Traffic light controllers, sequences managed using logic circuits. 9. Calculator functions, basic math uses combinations of gates. Each of these uses logic gates to make decisions, control actions, or process information based on logical conditions. Slide 8. XOR and XNOR gates. These gates focus on comparison logic. XOR, exclusive OR, gate. Output is 1 only when inputs are different. Boolean. Y equals a circle plus B. Example, a toggle switch, pressing either one changes the state. XNOR, exclusive NOR, gate. Output is 1 only when inputs are same. Boolean, Y equals a circle plus B closing parenthesis. Example, a sensor pair that only allows operation when both conditions match. Truth table. Significance. XOR is used in arithmetic and parity checking circuits. XNOR is useful in equality checking or error detection systems.